There are places on Earth that seem to stand outside time. A mountain ridge at dawn, a wall of granite above cloud level, a summit carrying snow older than memory. These are among the few things in the natural world that still feel, at first glance, beyond argument. Forests burn, rivers shift, coastlines retreat, cities rise and disappear, but mountains seem to belong to a slower order of reality. They feel less like events than facts, and yet that impression is wrong. The highest and oldest looking features on the planet are not fixed monuments. What looks permanent to us is often only a moment inside a much longer struggle. A struggle between forces pushing rock upward from deep within the earth and forces at the surface that never stop cutting, freezing, cracking, grinding, and carrying it away. Mountains exist not because one of those forces has won, but because for a time neither side has finished the job. That is the paradox at the center of this story. Mountains feel like symbols of endurance, yet every mountain on Earth is temporary. Some are still being lifted. Some are already losing height. Some are being carved down grain by rain, ice, rivers, and gravity. Some ranges that now look old and settled are, in geological terms, the worn remains of something far taller and more violent than what we see now. Once you begin to look at mountains this way, they change immediately. A mountain is no longer just a landscape. It becomes evidence, a visible expression of hidden energy, buried collision, internal heat, shifting crust, and long atmospheric attack. It tells two stories at once. One rises from below, where the planet folds, fractures, and thickens its outer shell. The other begins above, where weather and water work with astonishing patience against everything that has been raised. This documentary follows that hidden contest, not the complete history of every mountain system, and not a textbook survey of geology, but a narrower question. What actually decides whether mountains keep rising toward the sky, or are gradually worn back down into the earth? To answer it, we have to hold two opposite ideas in mind at once. Mountains are born through violence. Mountains are undone through persistence. They are made by forces powerful enough to lift continents, and worn down by forces so ordinary we live among them every day. Rainfall, frost, rivers, snowfall, landslides, thaw, gravity, time. Once that tension comes into focus, the shape of the world changes with it. The Himalayas stop looking like a finished wall of stone and start to look like an ongoing event. The Appalachian Mountains stop looking merely old and gentle and begin to read like the exhausted remains of a much greater upheaval. Even a quiet valley becomes part of the story, because valleys are often signatures of loss, places where mountains have already begun to yield. And so the real question is not simply how mountains are born. It is why they do not last, and why some seem able, for a time, to resist that fate. Stranger still, it is whether the very forces that destroy them can sometimes help keep them high. The deeper we go, the less this will look like a simple battle between building and erosion. It will begin to look more like a feedback system written into the planet itself, a restless negotiation between the deep earth and the open sky. If you stand far enough away from a great mountain range, it can feel almost absurd to imagine change. The scale defeats the idea. Mountain chains stretch across countries. Peaks rise through cloud decks. Ice clings to slopes through seasons and centuries. Human life, by comparison, is brief, local, and easily erased. A mountain outlasts empires so casually that it becomes tempting to treat it as part of the background of existence itself. Not something that happened, but something that simply is. That instinct is understandable. It is also deeply misleading. Mountains do not represent the end state of the land. They represent imbalance. They appear where the crust has been thickened, shoved upward, broken, heated, or otherwise forced out of equilibrium. Their height is not a sign that the system is at rest, but that something has happened to it, and may still be happening. A mountain range is less like a finished sculpture than like a frozen moment in a process too slow for human senses and too immense for ordinary language. We give mountains names and treat them as places. Geology sees them as episodes. The contrast becomes clearer when we compare ranges not by beauty or fame, but by what they reveal about time. The Himalaya, for instance, still look raw in a way that almost seems excessive. Their relief is extreme. Their slopes are unstable. Rivers tear through them with force. Earthquakes remind us that the system below them has not gone quiet. These are not merely high mountains. They are active mountains, still tied to a collision deep enough and vast enough to keep feeding the architecture above. They look permanent partly because they are so large. In fact, they are among the clearest examples of land still in the making. The Appalachians tell a different story. Today they do not dominate the horizon in the same way. Their forms are lower, rounder, older to the eye. In places they feel settled into the landscape, almost domesticated by time. But that gentleness is deceptive. These mountains are not modest because they were born modest. They are modest because they have been losing for a very long time. What remains is not the full force of their beginning, but the residue of it. Their current shape is a geological afterlife. That is where the mystery sharpens. If mountains can begin as violent upheaval and end as softened remnants, then the landscape around us is full of incomplete stories. Every peak is temporary height. Every ridge is a negotiation. Every valley may be the mark of ongoing removal. What appears solid is conditional. A mountain remains a mountain only as long as the upward forces that made it, or the structural legacy they left behind, are not fully overcome by the downward work of weathering, erosion, collapse, and time below the surface. The earth is not passive. Its outer shell is broken into moving plates. Deep processes generate pressure, heat, deformation, and uplift. At the surface, the atmosphere and hydrosphere are equally restless. Rain falls, snow accumulates, ice advances and retreats. Rivers cut, gravity pulls, seasons pry rock apart. None of this looks dramatic in isolation, but mountains are not erased in a single gesture. They are erased through repetition. So when we ask whether a mountain is rising or falling, we are really asking which side of that long contest holds the advantage. Is the crust still being pushed upward faster than the surface can cut it down? Has uplift slowed, leaving weather and gravity to inherit the landscape? Is the mountain in its explosive youth, its unstable maturity, or its long decline? These are physical questions, and the land itself is the record. This way of seeing mountains did not come naturally to human thought. For a long time, mountains seemed too immense, too ancient, too given to be understood as transient. But once that assumption began to break, the mountains changed meaning. They no longer marked permanence. They marked process. The more scientists learned to read folded strata, faulted crust, uplifted sediments, glacial scars, river incision, and deformed belts of rock, the clearer it became that the planet was not decorating itself with mountains from time to time. It was constantly building them, damaging them, and recycling them. That realization changes the emotional scale of the landscape. The mountain wall on the horizon is not outside history. It is history. It is the visible trace of forces that have not stopped acting just because we happen to be alive in the middle of them. Mountains seem to promise stillness. In truth, they are evidence of motion, which leads to the next question. If mountains are not permanent objects, but temporary outcomes, then what is powerful enough to raise them at all? What kind of force can fold, fracture, and lift so much rock that an entire continent acquires a spine? The answer begins far beneath any summit, in a world no human being will ever directly see. Beneath the landscapes we inhabit lies a planet that is neither still nor structurally simple. Its outer shell is broken into plates that move, converge, pull apart, and slide past one another over spans of time so long they blur ordinary categories of event and condition. Continents, which feel to us like the fixed stage on which history happens, are not fixed either. They drift, collide, and reshape the surface of the world. Mountains are among the grandest consequences of that hidden motion. Few examples make this clearer than the Himalaya. Seen from a satellite image, they look almost too deliberate, a vast arc of uplift marking the collision between the Indian and Eurasian plates. But the simplicity of the map hides the violence of the process. India, once separated from Asia by an ocean basin, moved northward over millions of years until the intervening oceanic crust was consumed, and continental crust met continental crust. That collision did not produce a neat line. It produced compression on an enormous scale. Rock layers were crumpled, faulted, thickened, and driven upward. Portions of crust were shoved over one another. Material that had once lain much deeper in the earth was forced toward the surface. The result was not only height, but instability, a mountain system still marked by stress, seismic danger, and ongoing deformation. What matters here is not simply that the Himalaya are high, it is that they reveal what mountain birth actually is. Mountains are not placed onto the surface like objects. They are made when the crust itself is changed, thickened until it has no choice but to rise, shortened until rock is forced upward, broken until old layers are repositioned into new geometries. Uplift is not decoration. It is structural consequence. When enough crust is compressed into too little horizontal space, the surface rises because it must. To modern viewers, this may sound settled, almost obvious in retrospect, but for a long time, the engine of mountain building was anything but obvious. Earlier generations of geologists understood many local details of folding and deformation, yet the larger system remained obscure. There were models in which the earth cooled and contracted, wrinkling its crust. There were theories built around vast sediment-filled troughs, later compressed into ranges. These ideas captured parts of the truth, but they struggled to explain the global pattern of mountain belts and the larger mobility of the planet. That is one reason the story of Alfred Wegener remains so compelling. In the early 20th century, Wegener argued that continents had once been joined and had later drifted apart. He saw in the fit of coastlines, the distribution of fossils, and the alignment of geological structures a clue that the present arrangement of land was not original. Implicit in that idea was a better explanation for mountain belts. Perhaps mountains form where continents move and collide. The problem was that Wegener could not convincingly explain how such massive bodies moved. He had a striking insight, but not yet the mechanism to make the scientific world trust it. Mountains were evidence waiting for a framework. That framework arrived gradually, through the work of many researchers and the accumulation of evidence from the seafloor. Earthquakes, crustal age patterns, and global tectonic structure. By the mid-20th century, the planet looked different. Seafloor spreading, subduction, transform faults, and plate motion transformed scattered observations into a coherent system. The Earth's crust was no longer a mostly static shell suffering local accidents. It became a dynamic surface made of moving pieces. And once that view came into focus, mountains stopped being isolated puzzles. They became consequences of plate interaction. The significance of that shift is easy to miss if it is told only as a triumph of theory. What changed was not just the answer, but the scale of the question. Mountain building was no longer about this valley or that fold belt. It was about the architecture of the entire planet. A summit in Nepal, a trench in the ocean, an earthquake zone, and an ancient deformed belt of rock could all belong to the same physical story. The hidden engine had been found. Not a single fire chamber under a single mountain, but a planetary system of moving plates, sinking slabs, rising material, heat flow, stress, and collision. And yet even here, the story does not settle into simplicity. Once we understand how much force the deep Earth can deliver, another question becomes sharper. If the engine below is powerful enough to lift whole ranges into the sky, why does it not simply keep building forever? Why do so many mountains end not in endless ascent, but in dissection, collapse, and loss? The answer waits at the surface, in processes quieter than tectonic collision, but no less consequential. Once a mountain rises, the sky begins working on it. Rain finds weaknesses. Rivers gather speed. Ice grips rock and tears it loose. Gravity exploits steepness. All the height won from deep compression becomes, at the same time, a kind of vulnerability. That is where the balance begins to shift, from fire below to weather above. That shift matters because the drama of mountains does not end when rock is raised. In many ways, it only becomes visible then. Height is not just an achievement of tectonic force. It is also an exposure. The moment crust is lifted into steepness, cold, wind, rainfall, ice, and gravity acquires something new to work on. Relief creates vulnerability. A mountain can only be attacked because it has first been built high enough to be attacked at all. The contrast is almost humbling. The deep earth works through collision, burial, heat, and compression on an immense scale. The surface works through things that appear ordinary enough to ignore. A storm passes. Snow settles into cracks. Water freezes at night and expands. A small fracture widens. A block of stone loosens. Meltwater gathers into channels. Channels become streams. Streams join rivers. Rivers carry away fragments so slowly, at first, that no single season seems to matter. Yet the power of surface destruction lies precisely in that repetition. Mountains are not usually defeated by one great blow. They are lowered by persistence. Rivers are often the first great agents of this inheritance. They do not merely flow off mountains. They reorganize them, Once uplift creates height and slope, running water begins to seek paths downward, cutting into weakness, exploiting fracture zones, and deepening valleys that divide one ridge from another. A mountain range that from far away seems like one continuous body begins, under the work of rivers, to separate into basins, walls, ravines, and isolated peaks. Sediment stripped from the heights is carried elsewhere, to foothills, to plains, eventually to the sea. What the mountain loses becomes part of another landscape. Ice adds a different kind of force, slower in movement but often brutal in effect. A glacier can appear from a distance, like something almost serene, a white mass occupying a valley with dreamlike stillness. But glaciers are moving bodies of ice armed with embedded rock, pressure, and time. As they advance and retreat, they scrape, pluck, abrade, and oversteepen. Valleys that rivers first began can be widened and transformed into deep U-shaped troughs. Sharp ridges and cirques emerge from repeated glacial carving. Glaciers do not simply preserve mountains under snow. They remake them. Then there is gravity, the most constant accomplice of all. Tectonic uplift can build steep slopes, but steepness is never neutral. The higher and sharper a mountain becomes, the more mass it places in unstable relation to itself. Rockfalls, debris flows, avalanches, and landslides are not accidents in the story of mountains. They are part of the logic of relief. A range that rises too quickly or stands too sharply begins to shed itself. This is one reason mountain landscapes can feel so paradoxical. Their beauty is often inseparable from their instability. Long before modern earth science had a full tectonic framework, some geologists were already learning to read this quieter side of the struggle. Figures like Grove Carl Gilbert helped change how landscapes were understood, showing that rivers, slopes, and sediment loads were not random details scattered across scenery, but parts of dynamic systems adjusting to one another. That shift mattered because it made erosion legible. It was no longer just a destructive afterthought. A landscape could be read as a record of competing processes. Seen this way, the mountain range stops being a monument and becomes a negotiation in motion. Every steep slope is an argument between uplift and removal. Every deep valley is a measure of how effectively the surface has cut into what tectonics produced. That is why the Appalachians matter so much in this story. They are not merely a second example after the Himalaya. They are the long answer to a question the Himalaya have only begun to ask. If the Himalaya show us what mountains look like when uplift still feels raw and forceful, the Appalachians show us what remains when surface processes have had immense spans of time to continue the work. Their rounded forms, forested slopes, and lower relief can make them seem gentle by nature. In truth, they are gentle by history. They are the surviving outline of an ancient collision, a mountain system once far higher and more dramatic, reduced through erosion across hundreds of millions of years. That transformation is difficult for the human mind to hold steadily, because our instinct is to grant permanence to anything that outlasts us. But geological patience operates on scales that strip that instinct of its authority, given enough time. Weather above does not need to overpower fire below in a dramatic sense. It only needs to keep working. By this point, it might seem that the balance has shifted decisively. The deep earth can build, yes, but the surface, patient and unrelenting, inherits the final word. Mountains rise only to be dismantled, and yet even that conclusion turns out to be incomplete, because in some cases, The very removal of rock from a mountain can change the forces acting beneath it. That is where the story becomes stranger. At first, the contest between uplift and erosion feels almost comfortingly clear. Forces below build, forces above destroy. One side raises the land, the other lowers it. But the Earth is rarely content to remain inside the first explanation that makes sense. The deeper scientists looked, the more they found that mountains do not evolve through a simple winner and loser struggle. They evolve through feedback. The key to that deeper layer lies in weight. Mountain ranges are not only high, they are heavy. When tectonic forces thicken crust and raise a belt of land, they create a mass pressing down into the softer, deeper material beneath. Remove some of that mass, and the system adjusts. This is the idea behind isostatic rebound. Unload the surface enough, and the crust can rise in response, as though a burden has been lifted. The Earth is more complex than any floating body metaphor suggests, but the principle is powerful. Erosion does not merely subtract height under certain conditions. It can trigger renewed uplift from below. That means destruction and creation are not always opposite motions. Sometimes they are linked phases of the same system. A river cuts down into a mountain range, removes enormous volumes of rock, and carries them away. The surface lowers in one sense, but the crust may respond by rising in another. The mountain loses material, yet part of the landscape is held high, or even lifted further because the load has changed. This possibility has become especially vivid in recent research on the Himalaya and on Chomolungma, the mountain many outside the region know as Everest. One striking argument proposes that changes in river systems, including river capture and accelerated incision in nearby drainage basins, may have increased erosion enough to contribute to renewed uplift through unloading and rebound. The claim is not that erosion simply made the mountain taller in any simplistic sense, nor that tectonic collisions ceased to matter. The Himalayas still owe their existence to deep crustal convergence. But the newer work suggests that surface processes may have helped shape exactly how high parts of the system now stand. That changes more than the mechanics. It changes the emotional geometry of the story. What had looked like a tragic inevitability, every mountain doomed by the patient work of weather, now becomes more ambiguous. The forces of removal may, in some circumstances, help preserve relief, renew uplift, or redirect the architecture of the range. Not forever, not universally, but enough to make the question stranger than it first appeared. This is also where scientific uncertainty becomes useful rather than inconvenient. Researchers do not agree on every detail of how strongly climate, erosion, and tectonics are coupled in every mountain system. There is broad agreement that climate matters, that rainfall and ice influence erosion rates, that erosion influences topography, and that unloading can affect crustal response. But how tightly these factors control one another, and in which settings, remains an active area of research. That disagreement is part of the story. It tells us that mountains are still teaching science how to think about them. Climate now enters the picture with new force. Rainfall is not just background weather falling on a pre-existing landscape. In some regions, heavy precipitation can intensify river incision, landsliding, and sediment removal. Glaciation can strip and sculpt at enormous scale. Storm patterns, monsoons, freeze-thaw cycles, and long climatic shifts all help determine how aggressively the surface attacks the uplifted land. Once that becomes clear, the atmosphere stops being scenery and becomes a participant. By now, the central question has changed shape more than once. At first, it seemed to ask what builds mountains. Then it became a question of what destroys them. Now it becomes something subtler. How do these forces interact so that a mountain range can rise, be cut down, rebound, and be reshaped at once? The answer is not a single mechanism. It is a system of linked processes operating across different scales of time. What emerges is not confusion, but a more earned complexity. The mountain is not the simple product of uplift minus erosion. It is the visible expression of their continuous entanglement. Fire below and weather above do not merely oppose one another. They compose the land together. Once that becomes clear, the meaning of mountains begins to widen. They no longer tell only a geological story about rock mechanics and plate motion. They begin to tell a story about time, impermanence, and the instability of things that appear most enduring. There is an old temptation, when looking at mountains, to imagine that they stand outside the ordinary rule of passing things. Human works decay quickly by comparison. Roads crack, towers fall, borders shift, languages change. Against all of that, a mountain can feel like a refusal. It remains while generations come and go. It seems to offer the rare comfort of something that does not need us and will not notice our disappearance. What geology reveals is not that this feeling is foolish, but that it is incomplete. Mountains do outlast us, often by staggering margins. But they do not stand outside change. They move at a pace that exposes the narrowness of human time. What appears eternal from within one lifetime may be temporary from within the life of the earth. A peak is not permanence itself. It is a long event. That is why the Himalaya and the Appalachians belong together in the imagination. One appears raw, towering, unfinished, still fed by a collision powerful enough to fracture continents and keep the crust in motion. The other appears subdued, almost reconciled to its own age, its original violence translated into rounded ridges and lower relief. Yet, neither is more truly a mountain than the other. One shows a system in its fierce upward phase. The other shows what remains when weather above has gone on working after the greater tectonic drama has quieted. Between them lies a demonstration of the full arc of mountain existence. James Hutton, centuries ago, intuited something profound in this. He saw that the earth was not a stage occasionally interrupted by change, but a system of continuous recycling, wearing down, depositing, burying, heating, lifting, exposing. In that sense, mountains are not exceptions to the rule of transience. They are one of its clearest expressions. They rise because the planet is restless, and they fall for the same reason. There is, perhaps, a quiet comfort in that once the first shock has passed. The fact that mountains do not last does not make them lesser. It makes them more interesting. They are not static symbols placed into the landscape like monuments. They are records. They hold traces of vanished oceans, buried collisions, ancient climates, glacial advances, river systems, crustal thickness, and the long argument between gravity and stone. To read a mountain properly is to understand that it contains more than height. It contains time made visible. That may be why mountains continue to affect human thought so strongly. We are drawn to them because they seem to promise endurance, but we remain with them because they reveal something truer than endurance. They show that even the grandest forms are provisional. That scale does not cancel change. That beauty can arise from instability. Seen from this angle, the central question has been quietly transformed. What decides whether mountains continue to rise or are worn back down? The answer is no longer a single force or a simple contest. Mountains rise where deep tectonic processes thicken and deform the crust. They are lowered by rivers, ice, gravity, weathering, and time. Sometimes erosion helps shape uplift itself through unloading and rebound. The fate of a mountain is decided not by one side alone, but by the shifting relationship among all of them. So in the end, mountains are neither the permanent monuments they first appear to be, nor mere victims of erosion slowly wasting away. They are something stranger than either of those ideas. They are temporary balances in a restless planet, places where hidden pressure from below and patient change from above meet, struggle, and for a time hold one another in view. That may be why they matter beyond geology. To study mountains is to confront a scale of time in which permanence turns out to be only a matter of perspective. What feels immovable to us is, in the life of the earth, still unfinished. What seems solid is still being negotiated. The ridge on the horizon, the summit in snow, the valley beneath it, all belong to processes that began long before us and will continue long after us, rearranging the land without hurry and without pause. There is something deeply human in being unsettled by that, and something equally human in finding meaning there. We live brief lives among forms that seem stable enough to anchor memory. Mountains become symbols because we need such anchors. Yet the mountain, when understood more fully, offers a harder and perhaps wiser lesson. Endurance does not mean stillness. Strength does not mean immunity to change. Even the greatest structures in the natural world are shaped by forces that build and undo them at the same time. And perhaps that is the broader question waiting beneath this one. Not only how mountains are born and destroyed, but what kind of world we inhabit if even mountains are temporary. The answer is not a bleak one. It is a living one. It means the earth is not finished. So the next time a mountain feels eternal, it may be worth remembering that what you are looking at is not permanence made visible. It is change made visible, lifted high enough, and held still long enough for us to notice